Okay, hello everybody. Welcome to this week 12 of problem solving session on control engineering. And today we'll be seeing problems on the topic that is design using state space. So our first question is, uh, so in this session, we'll be solving problems on the controllability and observability of a system and how we can uh, use state feedback and observers like for these systems, right? So let's begin by solving the simple question. So if you're asked to find the controllability and observability of a system, so this is the general form of a system. As you know, we have discussed in the last class. It's in this form: x dot is equal to ax plus bu, y is equal to cx, in fact, plus du. So this here we have a is equal to 0, 1, -1, and -2. B is equal to 1 and -1. C is equal to 1 and 1. And D is equal to 0. Okay, so now is the screen visible? Yeah. So now in order to check controllability, we make controllability matrix. So actually, there are two tests. We'll study both. As of now, let's study Kalman test for controllability and observability. Okay, so Kalman test for controllability. What does it say? You have studied it. I'll just write the formula. So Kalman's test for controllability says that make a matrix MathCal C, which is given by B, AB, A square B, so on up to an minus B. Check its rank. So if this C matrix is of full rank, then I pair AB or my system x dot equal to ax plus bu is controllable. And how do we check the rank of a matrix? We see number of linearly independent rows or columns, right? So for rank, we check number of linearly independent rows or columns. Correct. So in simpler words, so for okay, we will see that in a minute. Similarly, the test for observability goes like this: if the rank of my observability matrix, which is MathCal O, that's given by C, CA, CA square, so on up to CAN minus 1. If this is of full rank, then my system is observable. Whenever we talk of controllability, we talk of matrices A and B. And whenever we talk of observability, we talk of matrices A and C, right? Because controllability, and because whenever we talk controllability, we talk about input of a system, and input is linked with matrix B. And whenever we talk of observability of a system, uh, and observability is linked with the matrix C, right? So that's why sometimes instead of saying the system is controllable, I'll say pair AB is controllable. That means that the whole system is controllable. Similarly, instead of saying my system is observable, I'll say my pair AC is observable, right? So there you have studied these tests in detail. You might have gone through like through the slides or through the lectures, and you might have gone through these formulas. And here, let's just focus on problems. So we have a 2 by 2 system. So here we have a 2 by 2 system. Our matrix A is of 2 by 2. So therefore, our controllability matrix will only have two terms, B and then AB, right? So as per for the question. So now let's uh, go towards the question. So we'll make our controllability matrix that will be B and AB in our case. What's B? B is 1 and minus 1. What's AB? I don't know. Let's calculate. So my A and B is, my A is 0, 1, minus 1, minus 2, and my B is 1 and minus 1. I hope everybody is comfortable in multiplying matrices. Then it will be minus 1 and plus 1. Right, so therefore my mathcal C, it will be 1, minus 1, minus 1, and plus 1, right? So now let's see the rank. Or in simpler words, we check the determinant. So if I have a 2 by 2 matrix, if I have a 2 by 2 matrix, and if the determinant of this matrix is non-zero, then this matrix is of full rank. If the determinant is less than 2, then it means it's not full rank. Similarly, if I have a matrix 4 by 4, if its determinant is non-zero, it means it's of full rank. The rank is 4, right? But if the determinant is not 0, it means the rank is less than 4. It can be 3, it can be 2, it can be 1, right? Similarly, here in our case, we have a 2 by 2 matrix. So our mathcal C is 2 by 2. Now let's see determinant of mathcal C. What's determinant of mathcal C? It's 1 minus minus plus minus 1. It's equal to 0. So determinant of mathcal C is equal to 0. It means the rank of C is not equal to 2. It implies rank of mathcal C is less than 2 or is not equal to 2. It's indeed less than 2, but here we can say it's not equal to 2. It should be equal to 2. Therefore, our system is not controllable. Now let's look for observability. We have observability matrix O, mathcal O, that will be C and CA. Correct? So in some books, you might see C transpose, then A transpose, C transpose, A transpose square, C transpose. That makes things confusing. That's why it's better to use this notion C, CA, CA transpose, because if you take transpose of that, this will automatically come. So what's my C? C is 1 and 1. What's my CA? I do not know. So my C is 1 and 1. My A is 0 minus 1, 1 minus 2. No, what is it? Wait. 0, 1, minus 1, minus 2. So let's solve it. It will be minus 1, 1 minus 2. That will be again minus 1. right? So sorry, it will be this. This is 1 over 2. This is 2 over 2. It is 1 over 2. So it will be like this. Right, so therefore my CA is -1, -1. So therefore, let's check the determinant of this matrix, MapCallo. Determinant of MapCallo, it's -1, minus plus 1. It's again equal to 0. It's not equal, it's less than 2, or it's not equal to 2. Therefore, my system is unobservable. So here my system is neither controllable nor observable, but it's not the case. My system can be observable, not and yet not controllable, or it can be controllable yet not observable. There can be many cases. So let's solve now this question. Everybody please try. We have x dot equal to 0, 1, -20, -9, x, 0, 1, u, y is equal to 1, 0, x. Check controllability and observability. If you can see from this form, if you can see from the structure, it's already in controllable canonical form. Right. So it's already in controllable canonical form, but still you check. The system is of course controllable as well as observable, but still you tell me the value of the MathCal C matrix. This can be confusing. The rank can be less than 2. Everybody got controllable. Everybody got this CA matrix, MathCal C matrix. Yeah, it's both controllable as well as observable. So I'm leaving it as a homework. So similarly, you'll get system is observable. It's not difficult. It's an easy way to do it. One more question. So consider the following system. Consider the system. X dot is equal to 1, 1, 0, 1, x plus b1, b2, U. Similarly, Y is equal to C1, not C1, be confusing, yeah, D1, D2, X. Now the question is the conditions for complete state controllability and complete observability are option A. D1 not equal to 0, B2 not equal to 0, B1 and D2 can be anything. Similarly, D1 not equal to 0, start solving it. D1 not equal to 0, D2 not equal to 0, B1 and B2 can be anything.
So instead of writing this option, we have to solve.
Yeah, please solve it. So do you get any idea how to solve it?
Same now, what we have done in the previous case.
Yes, you do that, you'll get some condition and tell me that condition. I'll by the time I'll write options. You just write controllability matrix, find the determinant of that, and you see what condition you are getting in terms of D1, B1, B2, and B1. Similarly, you do observability and tell me what conditions you are getting. Yes, please solve it and tell me the solution. What did you get the determinant of Pascal C? Anybody calculated what is the
B1, B2.
determinant? Okay, you're saying the matrix or
Yes, this matrix, controllability matrix, I have got only minus B2 square.
controllability matrix, you have got B2.
No, that whole
Determinant.
determinant.
Determinant. Okay.
B1,
What is determinant?
B1,
B1.
B1 plus B2.
B1 plus
Second
B2.
element, next element.
Okay. Okay, sorry. Uh, okay, let me write it. Let me solve it. Let me solve for controllability, then you'll get an idea for observability. So my controllability matrix, it should be B and AB because it's a 2 by 2 system. Only two terms will be there. And my B is B1 and B2. And my AB is, when you solve it, you'll get B1 plus B2, and this will be B2. If anybody has any questions, please stop me and ask. So then this is my controllability matrix. Let's take the determinant of it. It will be B1, B2 minus B2 into B1 plus B2. So if we solve it, it will be B1, B2 minus B2, B1 plus B2, sorry, minus B2 square. This and this goes, and we'll get minus B2 square. It means for the system to be controllable, only B2 should not be equal to 0. B1 can be anything. So the controllability does not depend on B1. So B1 can be anything. So B1 can be anything, but B2 should not be equal to 0. Similarly, when you make observability matrix, similarly, when you take the determinant of observability matrix, you will get observability matrix equal to D1 square. It means for the system to be observable, D1 should not be equal to 0. Right? So D1 should not be equal to 0 and D2 can be anything. Right? So this is the correct option. So for the system to be controllable, B2 should not be equal to 0, B1 can be anything. For the system to be observable, D1 should not be equal to 0, D2 can be anything. Did you understand? You can get many questions based on this. Like you can get like similar type of questions where you get some A matrix like this. 0, A2, 0, 0, 0, A2, 0, 0, 0, and B matrix is B1, B2, B3. Then you are asked something. What are the different conditions uh, for the system to be controllable? Like what are the conditions on A1, A2, B1, B2, B3 for the system to be controllable as well as observable, etc. Right? So if you have any doubt, please tell me. Otherwise, I'll just move ahead and do this question which I was talking about. Okay, no problem. Now let's consider the following system. X dot is equal to AX plus BU, where A is same, whatever I was talking, A2, 0, 0, 0, and B is
Sir,
B1,
one
B2.
minute, sir.
Yes, yes, please.
Sir, in controllability, B2 is not equal to 0. And in
Yes,
observability, D1 is not equal to 0.
yes.
And resting anything can be happen. Na?
Now for this particular question, so
Yes, sir.
you have a specific A matrix.
Yes, yes.
Uh-huh. Somebody else was asking something.
Okay.
Okay. Okay. So now see this question. We're given x dot equal to x plus bu, where a is this 0, a1, 0, 0, 0, a2, 0, 0, 0. B is b1, b2, and b3. Correct? Now the question is for the system, okay, the question is the minimum number of non-zero elements in matrix B such that the above system is controllable. So the question is, we're given a system, x dot equal to x plus bu, a is given, b is given, and we're asked, so tell us what should be the value of b1, b2, and b3? Like the same type of question. Should it be zero or non-zero or whatever? So we are asked the question, minimum number of non-zero elements in matrix B such that the above system is controllable. So follow the same process and tell me the answer. Just find the controllability matrix, MathCal C, then find the determinant of that. You'll get some condition. Based on that condition, tell me the answer. Your controllability matrix should be B, AB, and A square B. So it should be B1, B2, B3. I compute AB. What's AB? Anyone? Or let me know. Anyone computed AB? Or if you want me to compute at least once, AB and A square B, or if you feel it's uh,
Yes,
straightforward,
sir.
then no need.
AB matrix.
Should I compute
Yes,
it?
yes, sir.
Okay. Okay, let's compute it, AB. So my AB is, for a 3x3 system, let's compute it. My AB is 0, A1, 0, 0, 0, A2, 0, 0, 0. So you should be very well versed with this matrix multiplication, because when you are solving a state feedback problem or an observer design problem, you will have to do these calculations at least 2 by 2 at least, because 3 by 3 I don't think they'll ask in exams, because otherwise, or they will give you a sparse 3 by 3 matrix where calculations become easy. Otherwise it's very difficult to solve by hand without calculators. Anyway, so we have this A matrix, and our B matrix is B1, B2, and B3. Correct? So now see, first of all, before you multiply, just see the dimension. It's 3 by 3, and this is 3 by 1. So your resultant matrix should
Sir,
be,
I have
so
got
see,
the answer of this answer.
okay, okay, can you tell
A1,
me?
A1, B2,
A1, B2,
second A2, B3,
A2, B3,
and 0.
0. So everybody got this, or you would want me to compute it? It's very straightforward. Just you have to multiply. Say, for example, so you'll have 3 elements here. So 3 columns here. So it should be 0 into B1 plus A1 into B2 plus 0 into B3. So you got A1 into B2. For the second row, 0 into B1 plus 0 into B2 plus A2 into B3. You got this A2 into B3. Similarly, 0, 0, 0. So it's straightforward. So we'll write it here. So A1, B2, A2, B3, and 0. Similarly, when you compute A square B, what you will get is, you'll get A1, A2, B3, 0, and 0. Now compute the determinant of this MathCal C. What is the determinant of MathCal C? This controllability matrix. So it will be easy to expand it each side. can expand it any side. So let me write it like this. A1, A2, B3, 0 minus B3, A2, B3. So it will be, this will vanish up to 0, or it will be minus A1, A2 square, B3 cube. Everybody understood what I did here? What I did is I just expanded it using this, right? So it will be A1, A2, B3, A1, A2, B3. Then you will have this, you will have to write determinant of this minor. So it will be B2 into 0, so 0 minus B3 into A2, B3, B3 into A2, B3. Is it clear? Now clearly you'll see for the
Yes.
system to be controllable, this all should be non-zero, right? So this whole should be non-zero. It means at least B3 should be non-zero for B1 from B1, B2, and B3, because the question is we have to see the minimum non-zero elements of matrix B. So we can conclude from here that at least B3 should be non-zero. Because if B3 is non-zero, if B3 is 0, this becomes 0, the system no longer remains controllable. But if B3 is not 0, and B1 and B2 can be anything, so they can take any value. So you can write it like this: B1, comma B2, they belongs to R except 0, right? So they take any value except 0. Sorry, they take any value. They can take 0 as well. There's no problem with that. But B3 cannot take 0, right? So the minimum number of, so the answer is the minimum number of non-zero elements in matrix P such that the above system is controllable is. Now, can you tell me what are the minimum number of non-zero elements in matrix
One.
P?
One.
1. So the answer is 1. So sometimes you are given these blanks. So the answer is 1, right? That is B3 should not be equal to 0. So I think with this, you should now be able to solve controllability and observability type questions that are given in your assignment. Now let's move towards some other types of questions that are there in your assignment. So let's consider the following system. So x dot equals to ax plus bu, y equal to cx. Here a is equal to 0, 6, 1, and minus 1. B is equal to minus 2, 1. C is equal to 0, 1. Can you quickly tell me whether the system is controllable or not? First, let's check controllability. Can you quickly tell me whether the system is controllable or not? Based on that, we'll form the different questions. It's not controllable. Ramya has said that it's not controllable. Anybody else got that it's not controllable? Okay, I'll write different questions. Question 1 is find whether it's controllable or not. Question 2 is find the eigenvalues of A. Okay, if you have done question number 1, go for question number 2, find the eigenvalues of A. Anybody who wants me to compute this? How to find the eigenvalues? Is the system controllable? Everybody got this? System is not controllable.
Yes, a metric is
Eigenvalues.
equal to 0.
Okay. Okay, it's not controllable, right?
Yes.
So please find the eigenvalues. Did you get these values?
What we have to do, sir?
So did you find the eigenvalues of matrix A?
Okay, we have to find it because we have written the answer.
Yeah, so anybody has any doubt how to compute it? So now see, there is another test for controllability, which is called PBH test. Papov, Bilevich, and Hodge test. It's a very powerful test because if you have a 5 by 5 system or a 4 by 4 system, it's very difficult to find a cube b, a raised to the power 4b, and so on. So it's very difficult. What does this test say? So for example, if my matrix A is n by n matrix, then this PBH test says find the rank of the matrix lambda I minus A B, right? So this is one column, this is other column. So my PBH test says find the rank of this lambda I minus A and B. If this rank is equal to n, then my system is controllable. Otherwise, system is not controllable. Now I'll tell you here this lambda belongs to C. Like it can take any complex value, any value. But like see, when can this be rank deficient? When can this matrix, this lambda I minus AB, when can this be rank deficient? When this part is 0, right? If there is any 0 term in B and this lambda I minus A part is 0, then this matrix will be rank deficient. Is that correct? So in that case, so see this, when can this lambda I minus A be 0? It will only be equal to 0 when my lambdas are eigenvalues of matrix A. Why? Because in that case, this will become characteristic equation, right? So this lambda I minus A, so when we find the roots of this lambda I minus A, so they are the eigenvalues of my system. So it means this matrix, this rank of lambda I minus A, B, this can only be rank deficient on the eigenvalues of matrix A. So you only need to check, you only need to put, so you don't have to put lambda any value in complex plane, you only have to put for eigenvalues, because only on those values this can be rank deficient, otherwise this is always full rank, right? So for example, in the given problem, we have a 2 by 2 and my eigenvalues are 2 comma minus 3. So I'll check for my system. So let's see. I'll find this lambda I minus a. Let's take, let lambda is equal to, first let's take 3. So then it will be 3 0 0 0 3 0 0 0 3 minus a is 0 6 1 minus 1. Sorry, it's 2 by 2 only. Zero 6 1 minus 1. So we will solve it and we will get 3 minus 6
Sir,
minus
you have
1.
considered lambda is equal to 3, sir?
Yes, I have this lambda is eigenvalue. I told you.
Okay,
Lambda
okay.
is any value in complex plane, but it can only be 0 when my lambda is eigenvalue. In that case, it will be characteristic equation, right? So
Okay.
that's why now I will see, I'll only check the rank at lambda equal to 2 and lambda equal to minus 3. Sorry, it should be minus 3, right? So minus 3. So then this will be minus 3 and this should be minus 6. This should be minus 1 and that should be minus 2, right? So I got this part. So now I need to check rank of minus 3, minus 6, minus 1, minus 2. And what's my B? Minus 2, 1. Minus 2, 1. What can be the rank of this system? At least it's 2 by 3 matrix, right? So the rank is at is 2 by 3. So at least the rank should be 2. At least it cannot be 3 because rank is minimum of n cross m, right? So if you see, if you check this, the rank of this matrix is equal to 2. Rank is 2. Therefore, lambda equal to minus 3 is controllable eigenvalue. You'll get things clear. We'll do the other part. Let's now take lambda equal to 2. Now see, 2 0 0 2 minus 0 6 1 minus 1. Now see what we can get. 2 minus 6 minus 1 3. So what is the determinant of this? What is the determinant of this matrix? 6 minus 6 equal to 0, right? Similarly, if you take determinant of this matrix, what is this? It's 6 minus, it's again 6 minus 6. Okay, wait.
So this is also controllable eigenvalue.
No, we'll have to check. Wait. Wait. Okay, let's see what's the matrix I will get. So we get lambda I minus A B. We get rank of lambda I minus A is 2 minus 6 minus 1 3, and here it is minus 2 1, right? So it's coming out to be same or not. You multiply it with 2. Okay, yes. So see, if you multiply this with 2, what we will get, right? Or minus 2, we'll get 2, we'll get minus 6, we'll get minus 2, right? If we multiply this with minus 2, what we'll get? 2 minus 6 minus 2. Is it correct? And here, is it possible to get this uh, first row from this second row? Look here. How do we check rank? For rank, we see number of linearly independent rows or columns. So in this case, let's focus on rows, right? So if I have to check rank of a matrix, I will look for number of number of linearly independent rows, right? So for example, I have to check the rank of this matrix. I look for the number of independent rows, but I can see my second row, it can be, or my first row, we can obtain this first row from the second row by just multiplying minus 2. So it means my first row is dependent on the second row. So it's not linearly independent, right? It's linearly dependent. So so at least for this matrix, it's rank deficient, right? It's not, the rank of this should at least be 2 because it's 2 by 3 matrix, so at least be 2. But since this first row is linearly dependent on second row, it means the rank is less than 2. So when the rank is less than 2, it's not equal to n, it's not equal to 2. It means my system is not controllable. But if you can see from this matrix, this rank is equal to 2. You can check this from MATLAB as well. So if you check the rank of this matrix on MATLAB, you'll get rank is equal to 2. And for this, you'll get rank is equal to 1. So it means this is for this eigenvalue, lambda equal to minus 3, my system is controllable. And for this eigenvalue, lambda equal to 2, my system is uncontrollable. Why? Because rank of this matrix, lambda I minus A B, it's full in case of lambda equal to minus 3, and it's not full in case of lambda equal to 2. So there are questions in your assignment where you have to find, uh, like you are given a system and you're asked to find the controllable eigenvalue or the uncontrollable eigenvalue. So this is one way. One way to do is this, like you'll find this matrix lambda I minus A and B and find its rank. Find rank. But find rank only on eigenvalues. Find the eigenvalues and use lambda or put lambda as eigenvalues. So if rank is equal to order of the matrix, then the eigenvalue is controllable. Otherwise, uncontrollable. right? This is one way. I'll show you another way in a moment. But tell me, is there any doubt in this question?
How did you solve this matrix rank 2 by 3
Okay,
matrix?
yes, yes, yes. Okay. Any other doubt?
No other, no
So,
doubt.
okay. So we have two matrices. One is this, other one is this.
No, below,
Okay,
just last. Yes.
this one. Okay. So there is no doubt in this. It's both rows are linearly independent.
One
So,
anyone you can explain.
yeah. Okay. So let me explain with this matrix. So, so what are linearly? What do you mean by linearly independent rows or columns? Right. It means if I cannot obtain that particular row from any other rows, right? For example, here I have two rows. So if I compare these two rows, I will have to see whether I am able to get any row from the other row. For example, let's assume I have R1 and R2. So if I am able to obtain R1 from R2 or R2 from R1, then these rows are linearly dependent. But if that is not the case, if I'm not able to obtain these rows from each other, then they are linearly independent. For example, if I have a row as 100 and my other row is a 102, let's assume I have this row R1. My other row is 204. This is R2. R2. My other row is uh, 10, 0, 20. Uh, 5, yeah, 10. Sorry, what I have multiplied here, 10, yeah, 20. So this is my R3. So I can see all these rows are linearly dependent. All these rows are linearly dependent. Why? Because if you multiply R1 by 2, you will obtain R2, or if you multiply R1 by 10, you will get R3, or if you multiply R2 by 5, you will get R3. So whenever you obtain rows like this, when there is a dependency between rows, then the rows are linearly independent. Then the rows are linearly dependent. But when you are calculating rank, so rank of a matrix is given by number of linearly independent rows or columns of that matrix, right? So that's why I only checked for this whether my these two rows, whether they are independent or dependent, and I found they were dependent on each other, because if you multiply row 1 row 2 by minus 2, you'll get row 1. So it means they're dependent. So when they're dependent, it means the rank is not equal to 2, because there is one dependency. So rank is equal to 1. But here, if you see, I cannot obtain, you do any multiplication or any division, you will not be able to obtain R1 from R2 or R2 from R1. So in this case, the rank is full. What is the maximum rank that this matrix can have? So if I have a matrix whose order is m cross n, where m is less than n, then the rank of this matrix can at least be m, minimum of m cross n. So that's why I said the rank can at least be 2, but yeah, the rank can at least be 2. And since there are no linearly dependent rows, so the rank is 2 in this case. Is that clear, or there is any other doubt?
Yes, sir. Clear.
Okay. So in these questions where you're asked to find the uncontrollable eigenvalue or controllable eigenvalue, you just follow this PBH test. PBH test. This is one way, right? Or if you have a single input, single output system like this. So if you have a single input, single output system, so you have single input, there's only one input here, one input and one output. So this is single input and single output. So you know, for single input and single output systems, the state space can be converted into transfer function, right? So you can easily convert it into transfer function by using C into Si minus A inverse into B. So when you get transfer function for this system, you will get like this. See, for the above system, the transfer function you will get like this: S minus 2, S minus 2, S plus 3. So for the above system, you will get this transfer function. But there is a pole zero cancellation, you see. One zero is getting cancelled with one pole, right? So the pole zero cancellation pair, that is the uncontrollable eigenvalue. This pole zero pair controllable, this eigenvalue, it's the uncontrollable eigenvalue. Or this is the controllable eigenvalue, right? So this is one way, because if you have a single input, single output system, or you just find the transfer function, you see there will be some pole zero cancellation if my system is uncontrollable, right? So there will be some pole zero cancellation, and the eigenvalue associated with that pole zero cancellation is the uncontrollable eigenvalue, and the remaining ones are the controllable eigenvalues. But I think this PBH test is much easier. You just have to check on eigenvalues and you're done, and you can just check this with MATLAB as well. So in exam, you can just cross-verify your answers using this. Is that clear? Now there is another way. There is another way of doing this. I'll show you. Now let's see something else. I don't know whether you have gone through your lectures or not. Have you studied controllable canonical, like controllability decomposition? Have you read that? Did they teach? Anyone? So they haven't like taught this canonical decomposition. Okay. So controllability decomposition. I'll tell you this thing. This is similar to what we learned in the earlier question. So if you have a system like this, x dot is equal to ax plus bu, y is equal to cx, right? And if this system is not controllable, if this system is not controllable, you can always find, like, see, for example, if there are three states, let's assume only one state is not controllable, other two are controllable. Or if there are four states, let's assume two are controllable, two are not controllable. As we saw here, one eigenvalue was controllable and other one was not controllable. So same can be the case here. Some states can be controllable, some states cannot be controllable. So in that case, if my system is not completely controllable, then we can always decompose that into the controllable and the uncontrollable part, right? So we can find, so if the system is not controllable, then we can find a matrix P such that P inverse is equal to AC A12 0 AC bar, and PB is equal to BC and 0, right? Where this AC and BC, this is the controllable part. And AC bar, this is not controllable part. Right? So this AC and BC, they are of compatible dimensions, right? So you will have to study. So they are of compatible dimensions. So when you do examples, you'll have to take that into account. So the nutshell is, if you're given a system which is not controllable, you can always find which is not completely controllable. You can always find the controllable and the non-controllable part. right? You just have to find this matrix P. I'll tell you how to find this matrix P, right? In that case, I get, then I can get this in terms of this controllable and the non-controllable part. Now let's do a question based on this. You have this in your assignment as well, similar questions. Let's assume you have x dot. Just try to understand. 1, 1, 0, 0, 1, 1, 0, 0, minus 1, right? And this is x plus your u is 0, 1, 0 u. Okay. Now you have to check whether my system is controllable or not. So when you check using MATLAB, you'll find your system is not controllable. So the rank of like my MathCal C, the rank of my MathCal C, it should be equal to 3, but it's equal to 2, which is less than 3. It implies here A comma B is not controllable. Okay. Now, first of all, I told you right away that uh, there are some questions where you're asked your eigenvalues are controllable or not. So can you first find the eigenvalues? So if we find the eigenvalues, you just cross verify these questions after this class because just try. Otherwise, it will be very difficult for you to understand. My eigenvalues for this matrix A, the matrix eigenvalues are 1, comma 1, comma minus 1. So there are 3 eigenvalues, 1, 1, and minus 1, right? So again, we will see which of these eigenvalues are controllable and which among these eigenvalues are uncontrollable, because we know the system is not controllable. So there are some eigenvalues which correspond to uncontrollable part and some eigenvalues which can correspond to controllable part. But one thing is for sure. So if my controllable part, so this system is 3 by 3. If my controllable part AC here, this AC, if this is 2 by 2, then I know the eigenvalues would be 1, 1, and they will correspond to this controllable part because here it's now clear. Similarly, then this eigenvalue associated with AC bar, it will be minus 1. Okay, I'll come to this later. But as of now, what we are focusing on, we are just focusing on finding the controllable as well as the non-controllable part. So we did PBH test, but this is another way of doing it, and it's called canonical decomposition, right? So what I told you, so whenever you have a system which is not controllable, you can always find a matrix P, right? So you can always find a matrix P. But now how to find this matrix P? First, let's write this controllability matrix. What will be my controllability matrix? It will be B, AB, and A square B, correct? Or it will be 0, 1, 0. So when you compute it, it's not difficult. You just compute it. When you compute it, it will be 0, 1, 0, 1, 1, 0, and 2, 1, 0, right? Then what you have to do? We have to find P, right? So we have to find P. How we can, if we find P, then our task is done, because then P and P, we have to find P, and that will be invertible, of course. Then we are done. Then PAP inverse will get this, PB will get this. But the process is, there is this P can be found from P inverse, and there is a process for P inverse. So we'll find P inverse, and then we'll take the inverse of that P inverse, and we'll land to P. Now, how to get this P inverse? This P inverse is computed by using the first 2 rows of the controllability matrix. So you take the first two, sorry, columns of the controllability matrix. So 0, 1, 0, 1, 1, 0, right? I took the first two columns of the controllability matrix, and they form the first two columns of the matrix P inverse. Now, what should be the third row? So please pay attention because there is one question. There are a lot of questions which are based on this in your assignment. So in making P inverse, I took first two columns of this controllability matrix. Now, my third column, it is arbitrary. You can choose it, right? But you have to choose it in such a way that all the three columns should be linearly independent. They should not be dependent on each other. Why is that so? Because if you choose a column which is linearly dependent, then my P inverse will not exist. So if my P inverse will not exist, because my determinant in this case will be zero, P inverse will not exist, how will I find the P matrix P? So that's why you have to make sure you have to choose the third column in such a way so that all the three columns, they are linearly independent, right? So let's choose, it's arbitrary. I told you in the beginning, whenever we are doing design problems that can have n number of solutions, right? And all of them are correct. And mostly if it is given in the assignment, you'll be specified this third row, what you have to take. So in this case, if I take this third row as 0, 0, 1, then I can see all the three columns are linearly independent, right? So
Sir, how you choose this column?
I just made sure this column is not contained in this or not contained in this. It's arbitrary. I can choose any other column, but I choose this one. Why? Because this is the simpler one. So what would have been my second try? This 0, 0, 1, right? 0, 1, 1, my second try. Because again, 0, 1, 1 again is not contained in any of these other rows. See, if you multiply this column with anything, can you get this column or this column? No, right? You cannot get it. So that's why this column is linearly independent. Okay, so I told you it's completely fine if you take anything as long as your columns are linearly independent and your P inverse exists. Okay, for the sake of easiness, so that my calculations become easier, I took two zeros and one, right? So
Yes, sir.
yeah, okay. So now I got P inverse. If I take the inverse of this P inverse, so my P is equal to inverse of P inverse, which is equal to, you take it from MATLAB, your P should be equal to -1, or using calculator. Calculator also gives this inverse 0, 0, 1. So this is your P. Now your job is done. You just multiply this P into A into P inverse, and what you will get? You'll get something like this: 0, -1, 1, 1, 2, 0, 0, 0, -1. And your PB is 1, 0, 0. Now see, I'll write again it here. I told you when AP, sorry, just try to understand. PAP inverse, it should be equal to AC, A21, 0, and AC bar. Similarly, PB should be equal to BC and 0, right? Now let's identify AC, right? So 0, you see, this is 0. This is my 0. Okay. So this part is 0. Now, what is my A21? This is my A21. This is my AC. And this is my AC bar, right? And how can you identify this? You can identify this from the dimension of zeros. See, the dimension of zeros is 1 cross 2. So this AC bar, the number of rows in AC bar has to be the same as that of 0. This is very like common sense. You should have this. So the number of rows in AC bar is exactly equal to this, the number of rows in the zeros. Right? So there are number of rows in the zeros is 1. Therefore, the dimension of AC bar is 1. Right? Similarly, similarly, the number of rows in A21 should be exactly as same as that of AC. So you see, that's why AC is 1 comma 0. Right? So similarly, what is BC? Similarly, the dimension of BC should be equal to the number of rows in BC should be exactly equal to the number of rows of AC. So this is my BC. So my BC is 1 comma 0, and here is the 0. This is 0. So I found it. I did this transformation. You see, I found a P matrix such that my system is converted into this AC A12 0 AC bar BC and 0. Exactly, I'm getting this transformation. Now this is my controllable part, and this is my uncontrollable part. Now this, let's assume this AC. This AC is 0 minus 1 1 2, and BC 1 0. If you see this pair, this will be controllable. And if you see the eigenvalues of this AC, it will be 1 comma 1. Right? Similarly, now see, this is the uncontrollable part. So uncontrollable part, AC bar is equal to minus 1. The eigenvalue will be minus 1. So this is other way. This is other way of solving the same question which we solved using PBH test. What you can do, you can this is also called this finding this matrix P. This is called similarity transformation. You just read it. There is one very good book. I'm mentioning it here. C.T. Chen, Linear Systems Theory and Design, Chapter 6. So from this book, you can read Chapter 6. Right? So there you can find this. I think maybe they have covered this in the NPTEL lectures as well, but I did not see that. But yeah, this is very, very important because you have questions in your assignment based on this. So there is one question where you are given that, okay, find whether the system is controllable or not. Okay, the system is not controllable. If the system is not controllable, take the first two columns of your controllability matrix and make it make a matrix T, right? And the T should contain the first two columns of T should be the first two columns of controllability matrix, and then take the third column of T as 001 or anything 010, as long as the matrix T is invertible and the columns in T are linearly independent. So after that, you can do this TAT inverse. You'll get that in terms of controllable and uncontrollable parts, right? And after that, you can check, okay, my controllable part is this, my non-controllable part is this, right? So is this clear or there is any doubt in this? Yes? Anybody has any doubt in this or wants me to explain again? So forget about checking the controllable eigenvalues or uh, non-control uncontrollable eigenvalues. If you are just asked decompose the system into controllable and non-controllable part, just do this. This is called similarity transformation. You just have to find the matrix P. So, but there is no way to find P directly. You'll find P inverse, and by taking the inverse of P, P inverse, and then you'll find P. Then do this stuff, and you'll get the answer, right? So, should we solve another question?
Yes, sir. Tomorrow there is also lecture, sir.
Yes, there is one lecture tomorrow. I'll see what I should cover in that. Probably I'll just revise the whole control. I'll try to get one or two questions from every week and make 1 2 hour lecture.
Okay, sir.
Will that be okay? Or yeah, I think that should be fine because many people they haven't joined like for the whole duration, so it will be better for them as well. When is the assignment submission deadline for this week?
Wednesday.
Okay. So basically, in your assignment for this week, one question is based on controllability and observability, and that's very easy. And we did questions regarding to that, uh, according to that. And the other one is based on controllable and uncontrollable eigenvalues. You can use PBS test, or you can use this controllability decomposition, and often, at the last, you can use MATLAB. So this was number next. Third type of questions, I think, yes, it was based on this uh, controllability decomposition. But it's explained, the question is given in a very, very easy form. So everything is given from their end. You just have to be very careful while solving. So if you read from any good book, so you can just uh, say, like, just by seeing at the question, you can say, okay, this system is controllable and the system is not controllable. For that, you just have to uh, read more. So that's why I referred this book. This is a very, very good book. Just go through this. This will explain you what actually is controllability, what actually is observability, not limited to this Kalman's test, where we only as of now, I haven't even told you what actually controllability is. We're just focusing on problems. But controllability is not about this matrix B, A, B, A square, B, and so on. It's not limited to that. It's actually related with the input and how it is related and what are some what's its physical significance, and also everything is given in this book. Take some time and just read this book. So at least 6 chapter you should read about controllability, and also we'll do some questions on state feedback where we'll be doing pole placement and observer design. I'll do questions on that as well. So let's do one quick question based on this controllability decomposition so that it's more clear. Or let's do that at the last. First, let's do the questions on state feedback and observer design because they're also very important. So now let's say you are given a question. You're given a matrix. So whenever I'm saying you're given this A matrix, it means your system is x dot equal to ax plus bu, y equal to cx. So I'm directly saying this 0, 1, 9, 0. So this is your A matrix. This is your B matrix, 0, 1. This is your C matrix, 1, 0. Okay. So now the question is, wait. Design a control law u equal to minus kx, where k is equal to, since it's a 2 by 2 matrix, k1 and k2, such that closed loop poles are placed at -3 plus minus J3? This is one question. And after that, okay, we'll see after that. The observer design question, we'll see after this. So first, let's see this question. See, these type of questions you can easily solve using MATLAB. This is called pole placement. I'll tell you how, but first let's solve it. So the question is, this is your A matrix. It has some eigenvalues, maybe stable or unstable. But the the problem is normally you are given systems which are unstable, like which have eigenvalues in the right half plane, right? And then you're asked, can we design a control such that we can place the closed loop poles in the left half or anywhere in the left half? What are the conditions that we can place the poles anywhere in the left half? If we can place the poles anywhere in the left half, that means we can stabilize the system, right? Or if already I have poles in the left half, I can place them more far away from the origin so that I can improve the stability, right? So this is called pole placement, and it's only possible when my system or when my matrix is A and B, when they are controllable. So here they are saying design a control law where such that closed loop poles are placed at this. I can only design this control law if and only if my pair AB is controllable. So this is a condition for this. If my A and B pair, they are not controllable, I cannot design, I cannot place these poles. But since in the question it's already given place, it means system is already controllable. One thing. Second thing, you can see the system is in controllable canonical form. So it's automatically controllable, right? So we don't need to check it. So this is the condition that A and B should be controllable. Now, next, how to proceed? So it's given here that my poles should be placed at -3 plus minus J3. So my desired poles. So first we'll write desired poles. They should be at -3 plus minus J3. So based on this poles, can I write the characteristic equation? Right? So can I write my characteristic equation? S plus 3 plus J3 into S plus 3 minus J3 equal to 0. Can I write like this? Because then my poles will be S equal to -3 plus minus J3. That's it. Okay. So after this, let's solve it. So how to solve it? How to solve it? See, this is very easy. You can take this as A, B, A, B. So my formula is A plus B into A minus B. This should be equal to A square minus B square. Correct? So if I solve it, what I get? A square plus B square. Sorry, A square minus B square, which is equal to S square plus 9 plus 6S minus, what is this? It will be 9 and J square is -1. So it will be -9. Is that correct? Then it will be S square plus 6S plus 18. Anybody has any doubt here? Is it clear until here? So you just have to identify the desired poles, write them as a characteristic equation. And after that, just get this equation. So this is my desired characteristic equation. I should get this. Now, what do I have? Then after this, you just have to find ACL, which is equal to A minus BK, right? And what is your A? Your A is 0190. Your B is 01. Your K is K1, K2. So can I write it like this? 0190 minus 00 K1, K2. Is that okay? Anybody has any doubt until here? I just multiplied it. Why? Because this is 2 by 1. This is 1 by 2. So my resultant will be 2 by 2. If you have any doubt, please let me know. So let's solve this. What we'll get? We'll get 0. We'll get 1. 9 minus K1. And this should be minus K2. Okay. So now this is my ACL. This is a closed loop. Now what I have to find? I have to find SI minus ACL, right? So now what's this? S00S. This is SI minus ACL. This is 0, 1. 9 minus K1 minus K2. You simplify this, what will I get? I'll get S minus 1 minus 9 plus K1, and this will be plus K2. Okay. Now let's make the characteristic equation SI minus ACL. So what will my characteristic equation? It will be K2 into S minus, it will be S minus S plus K2. Yes, is it correct? It should be S plus K2. Now let's take the determinant. It will be S square plus K2S minus into minus plus. So it will be minus, or I like this, minus 9 plus K1. So it should be equal to S square plus K2S minus minus plus K1 minus 9. Is it clear? So this is what I got from a closed loop. And my desired was S square plus 6S plus 18, right? So this is my desired. So just compare the coefficients. Comparing coefficients, what I get? K2 is equal to 6 and K1 minus 9 is equal to 18. It means K1 is equal to 27. Therefore, it implies my K, which is equal to K1 and K2, is equal to 27, 18. So if you use K is equal to 27 and 18, you should be able to place the poles at minus 3 plus minus 3J, right? So if your K1 is 27 and K2 is, K2 is 6. K2 is 6. So then you should be able to place the poles at minus 3 plus minus J. But see, this is again huge computation. In MATLAB, we would just use this command. K is equal to place A, comma, B, comma, minus 3 plus 3J, comma, minus 3 minus 3J. You will get K is equal to 27, 6 right away. So instead of doing this whole calculation in MATLAB, you can just use this command, and you can, or in this way here, you can just get your calculations checked, just put A, just put B, and uh, put the poles. These are the desired poles, pole locations, desired pole locations, right? So if you have a 3 by 3 matrix or a 4 by 4 matrix, and if you have to use a state feedback, because in your assignments, I think you can use MATLAB, but in your final exam, I don't think they'll give 3 by 3 questions. These type of questions are only possible in exams, so in assignments. So in your exam, it will be very difficult for you to solve a 3 by 3 problem by hand. So, but in your assignment, you can use MATLAB. So straight away you use this place AB -3 plus 3j -3 3j, and you'll get the answer. Correct. So, now will you be able to solve the problems on state feedback if you are given any question? There are questions, so 3 by 3. You can solve them by hand. We will solve one 3 by 3 problem as well. You can solve them by hand, or you can directly use this command. You'll get the answer, right? So now let's do one more problem on this. Now you will solve it and solve it quickly because we have to do some other questions as well. So your A matrix is 0, 1, -1, 0. Your B matrix is 0 and 1. Find K equal to K1, K2. Sometimes you are asked this K1 or K2. So in that case, you'll eventually have to solve it. Find K such that my closed loop poles are placed at -1 and -2. Yeah, quickly. What will be the desired characteristic equation? Desired characteristic equation. That will be S plus 1 into S plus 2, which is equal to S square plus 3S plus 2. Okay, this is my desired characteristic equation. Now let's find ACL. ACL is A minus BK. My A is 0, 1, -1, 0. And my BK, B is 0, 1. So it'll again be 0, 0, K1, K2. Okay. So when you solve it, your ACL will be 0, 1, -1 minus K1 minus K2. Now what you have to do, SI minus ACL, you have to take the characteristic equation of that, right? So it will be characteristic equation of S -1, 1 plus K1, S plus K2. When you solve it, you get S square plus K2S plus K1 plus 1. And my desired was S square plus 3S plus 2. It implies my K2 is 3 and K1 plus 1 is equal to 2. My K1 is equal to 1. It implies my K is 1, 3. Anybody has any doubt in this? Please ask. So this was state feedback. Now, similarly, you are asked to find the gain L of observer such that your closed loop poles are placed, so on and so forth. Okay. So for example, for the same question which we did earlier, we had A as 0, 1, 9, and 0, B as 0 and 1, C as 1 and 0. So the question is, design a full order observer, design a full order observer with the observer poles at S equal to -12 plus -12j. Then the observer gain matrix L is equal to L1, then the observer gain matrix L1, L2 is equal to, right? So again, we're not going in the details of theory. I'm assuming you know what's an observer, why do we need to design it, or the theory behind this, and what's the structure of the observer. I'm assuming you know everything. So that's why you just have to go through the lectures. So now what we have to do again in these questions, you have to find the, again, you'll start with desired pole locations. Desired pole locations. My desired pole locations are S plus 12 minus 12j into S plus 12 plus 12j. Solve it. I told you how to solve it. A plus B into A minus B, and you'll get S square plus 24S plus 288. Now here you are now, the next step is you have to find a closed loop, which here is A minus LC, right? So your C here in this case, your C is 1, 0. The dimension is 1 by 2. In order for your system, in order to have a compatible this multiplication, the dimension of L should be 2 pi 1. So it should be something like this. A is 0, 1, 9, 0 minus L1, L1, L2, 1, 0, right? Then again, you'll follow the similar process. You'll get something like this. 0, 1, 9, 0 minus, just multiply it, L1, 0, L2, 0. Then you'll find this ACL. You'll get some matrix. Then you will find SI minus ACL, the same process. You'll get some characteristic equation. You'll compare that characteristic equation with this equation. You'll get the values of L1 and L2. It's exactly the same as we did in the state feedback. Is that okay? Will you be able to do this? Why I left this as a homework, because we'll do one 3x3 problem, and that might take some time, right? So you just do this. It's very easy. If you have understood state feedback, observer design is not a big deal. Now let's do this problem. This is a very, very good problem, and it's a 3x3 problem, and it might take some time if we are solving it theoretically. So homework. Very easy. It is actually same. Now let's assume you are given a matrix as 0, 1, 0, 0, 0, 1, -1, -5, and 6. B is equal to 0, 0, 1. In your assignment, you have a similar question and you want to design a state feedback U is equal to minus Kx such that your poles, closed loop poles are at S equal to minus 1 plus minus J2 and S equal to minus 10. The difference between your assignment question and this question is this term, right? There it's minus 6. Here I have taken 6. So be very, very careful here. So see how I solve it, and accordingly you'll solve your assignment question. Again, we'll follow the same step. So number one is write the desired loop poles in the as a characteristic equation. So I'll write S plus 1 minus 2j. Again, S plus 1 plus 2j. S plus 10. This is equal to 0, right? This is my desired characteristic equation. Okay, so now I told you again, you can solve this A minus B into A plus B. It will be A square minus B square. So let's solve this part first. So what it will be? A plus B whole square plus B square, and J square is minus 1 and minus 2 minus 8 will be plus. So it will be S square plus 2S plus 5. Then putting it there, so my desired closed loop characteristic equation will be S plus 10 equal to 0. And if you solve it, what you'll get? S cube plus 12S square plus 25S plus 50. So this is my desired closed loop characteristic equation. So done. Number one step is done. Now, number second thing is what you have to do. You have to find a closed loop. And what is a closed loop? It's A minus BK, right? So let's find it. So first of all, let's find BK. My B is 0, 0, 1, and my K is K1, K2, and K3. So what this is 3 by 1. This is 1 by 3. The multiplication is compatible. The resultant will be 3 by 3. So this matrix will be 0, 0, 0, 0, 0, 0, K1, K2, and K3. This is my BK. Okay. So now A minus, my A closed loop is 0, 1, 0, 0, 0, 1, minus 1, minus 5, plus 6, minus 0, 0, 0, 0, 0, 0, K1, K2, and K3. Okay. Just solve it. When we solve it, what we get? My ACL, very simple. So why I have taken this example? Because this is already in controllable canonical form and it's very easy to solve because my matrix A is already a sparse matrix. But you'll see when your A matrix is not a sparse matrix, it's very complicated. So if either you're given a sparse matrix where it's already in controllable canonical form and it's easier to solve, otherwise, you are given a 2 by 2 system, right? So my ACL is 0, 1, 0, 0, 0, 1, minus 1, minus K1, minus 5, minus K2, 6, minus K3. What's my next step? My next step is to find the characteristic equation of SI minus ACL. Okay, which is equal to S 0, 0, 0, S 0, 0, 0, S minus this whole ACL, right? I'm directly writing it now. What I will get, this for which I will have to write the characteristic equation. It will be like this: S minus 1, 0, 0, S minus 1, 1 plus K1, 5 plus K2, S minus 6 plus K3. So this is the matrix. And for this matrix, you have to find the determinant. So can anybody tell me how to find the determinant? There are many ways. You can evaluate using any row, but the simplest one would be to evaluate like this from this row, right? So find the determinant. It will be 1 plus K1. Then you see this, this. So this will be minus into minus plus 1. And then this will be minus 0. No need to write. Then minus 1. Second term. My second term. For my second term, I'll have to write S into minus 1. So it will be, my second term is minus 5 minus K2 and S into minus 1, that's minus S. Similarly, my third term is S minus 6 plus K3. Again, you'll multiply these two. It will be S square. Okay, so there's no need to write it like this. Into S square. So if I solve it, what I get? I get K1 plus 1. It will be plus S into minus 5 minus K2 plus S square into S minus 6 plus K3. If we simplify it, I get S cube plus K3 minus 6S square plus 5 plus K2 into S plus 1 plus K1 is equal to 0. Now, what was my desired? Desired was S cube plus 12S square plus 25S plus 50. Yeah, this was my desired. Now comparing coefficients. What do we get? We get K3 minus 6 equal to 12. It implies K3 is 18. Similarly, 5 plus K2 equal to 25. It implies my K2 is 20. 1 plus K1 is equal to 50. It implies my K1 is 49. It implies my K is equal to 49, 20, and 18. So if you use K, again, in MATLAB, use this. K is equal to place A, comma B, comma over the poles where minus 1 plus 2j, comma minus 1 minus 2j, comma minus 10. So you'll get this answer same. Is it okay? Any doubt in this? So in your assignment question, the question is similar, only here it's a minus 6. Here it is a minus 6. Use minus 6 and solve this, and you'll get some different, maybe some terms will be same, but yeah, some term will be different. Have you got an idea like how you can solve such questions? Again, if you're given design an observer, like for the similar question, if you are given design an observer, what you have to do, instead of K, write L, and then instead of, okay, let me mention here. For observer design, your ACL becomes A minus LC instead of A minus BK. That's it. Rest follow the procedure. Everything remains the same. Okay. Any doubt? We have a class tomorrow as well. So that will be tomorrow will be our last class. So any doubt or in particular, if you have a problem in solving any of the questions mentioned in the assignment, so please tell me. Otherwise, we can just stop the lecture. Or in general, if you have doubt in today's session in either similarity transformation or this controllability, observability, PBS test, or how to design state feedback and this observers, please let me know. Okay, so I think, okay, it's clear. Then let me stop the meeting, but I would want to learn from you, hear from you that uh, have you received the marks from the previous assignment, of the previous assignment?
Yes, sir.
Okay.
I got 92%.
Yeah, that's great. Yeah, I learned that. So anybody else who got good marks in the last assignment?
But I'm worrying about this assignment basically.
So what
It
is the
was not,
problem in this assignment? Please tell me.
was,
I can help you in that.
I was not able to go through the syllabus of this unit basically.
That's fine.
So
So that's what I'm telling. So see, you're. I'll just recap what's in the assignment. First question is based on controllability and observability. So nothing. There is nothing like difficult. Just apply Kalman's test, like C, CA, so on, or B, A, B, so on. So this is first question. It should be very easy, right? Second question is based on similarity transformation. Then that's given in detail. The question is explained in a very nice way. So then plus the questions which we did for similarity transformation, I think that should be clear. That was number two. The number third question is you have to find the controllable or uncontrollable eigenvalue. Again, I told you either you can use PBH test, which is lambda I minus A B. You just have to calculate the eigenvalues, then put the eigenvalue here, find the rank. So either you can use that or you can find the transfer function, or you can use the controllability decomposition similarity transformation. So like in the worst case, you can use MATLAB to verify your answers. The next part is just to find the state feedback. There is one question, one similar question, which we just now did. This question, this is for state feedback, and another question that's for observer as well as a state feedback. And that's it. There is nothing difficult. I think the most easiest question. Yeah, it may be uh, uh, like there may be more calculations, but in general, that's very easy.
okay, sir. We upload
So,
this
but uh-huh.
video on the you upload this recorded video so that
Yeah,
we can.
I'll just upload it. I'll just upload it right away,
Yes, sir, yes.
as well as notes. Like when is the last day to submit this? Wednesday?
There are 2 days more. I think on Wednesday. Wednesday.
Okay.
No.
Okay.
Yes. Wednesday.
Okay. So what I would suggest is everybody try to solve that assignment today. So if you face any difficulty, you can ask tomorrow because tomorrow we have a
Yes.
class.
Sir, yes,
So you can
definitely.
ask tomorrow, number one, and number two, we can you can ask any other doubt tomorrow as well. So better is first to solve this assignment, because it's normally not taught in BTech or normal control courses. This is a bit advanced part, but again, I'm here to help. And if you have any problem, we can discuss tomorrow. But please try after watching this lecture, after going through the notes, just try. I think you should be able to do all the questions.
Yes, sir, yes.
I'll just upload it in a minute, like maybe 10 minutes, just after this meeting.
Yes, sir, yes.
Okay, yeah. Thank you so much. So I'm stopping the recording.
Thank you. Thank you very much.
Tomorrow's session will be same time.